Thank you all for coming to this very exciting training. Whenever you're ready, take it away.
All right, thanks. So this is an introduction to machine learning for statisticians, and it's very high level. We will do some hands-on, but not too much. So this is, if you want to follow along, put the code that makes these slides on the GitHub. You can either copy that link. You could also just navigate in Google GitHub. Maybe the right place. Repositories. All right, so you can down. So here's the link again. Link. And then here's what it looks like. And you can download it and then open it in RStudio and follow along if you want. So this is basically the lecture in Quarto. All right, so you might be able to follow along just by typing with me. All right, so let's get started. So this is what we're going to be doing. I'm going to motivate machine learning, then give you some terminology and statistical framing. Terminology that's used in machine learning is sometimes confusing if you're used to hearing statistical vocabulary. I'll try to make the connection. But then I also write the entire lecture. I'm going to be talking about statistical models and expected conditional expectations, conditional probabilities, things that as statisticians you should be familiar with, because it's a very natural way of explaining machine learning. So I'm gonna give an important concept, cross validation, and then a very quick review of a few very different algorithms that are very commonly used and actually some of them pretty powerful. But there's hundreds of these things. So I'm just covering them just to give you a flavor of different ideas. But we're not going to be covering these in much detail. And then I'll show you, we're actually going to do a real exam. So if you have access to these slides, which is, you get the code, you have the slides. There's a book that explains all this in more detail and has code and has exercise. So you can go to the book, clicking on there, and there's a machine learning section. And one of the things you can do with this book too is it has a little GitHub link. You go get the code for any of the chapters that you want, and then follow along reading as you type code or run code up in R, so you get a sense of what's actually happening. All right. So what we won't cover, you won't just be disappointed if you came wanting to learn some of these. I'm not gonna go into too many of the details of the algorithms. There's just so many. I could take the whole hour and a half explaining random forest, for example. We won't be doing that. At deep learning, we're not covering that's one of the many algorithms that are out there. And then the Python tools, I'm not going to show you. I'm going to show you simple ones in R that are not as fast or powerful, but if you're doing a simple machine learning exercise, they're pretty good, pretty easy to implement. All right, so these are the packages that you need to install if you want to be able to run the code that I'm showing. So, and if you want to follow along, you should go ahead and install some of these before you start. So if you have the code, you can copy and paste this into R, and they'll all be installed. So the main one we'll be using for machine learning is this one. I'll be talking more about that one. And then DS Labs is a package that has examples. Okay, so here we go. So the motivation. Then in our world, we often some of our collaborators often have machine learning challenges. Some are pretty simple, others are more complicated. An example we're working on now is predicting cancer from cell-free circulating DNA. You get many genomic readouts, and you have from blood. If the person has cancer, some of those little molecules will come from cancer and might have a signature in them that you want to find, and then you see it in the future, you want to predict it. That's a hard one, but it's machine learning challenge. And there's other ones that I'm sure some of you have encountered, but the tools we're learning today are appropriate and can be used for simple examples. In fact, and the one I'm going to show you isn't that simple, and you can already do pretty well. And this is a very widely used example in machine learning lectures. It's the MNIST data set. And what we try to do is we try to read from an image, have an algorithm tell us what digit it is. So it's what's used in zip code readers, for example. So here's an example. You see this is an actual image, handwritten by humans. And when we see those three, we can immediately see it's 1, 5, and 9. So what we're going to do is we're going to write an algorithm today that can do that automatically. So we'll go through the steps of how that's possible. And then we'll try to make connections to things you might see in cancer research applications. All right, so how do we even start? How can we even do anything with these? These are images. So the first step is that it's digitized. So it's data now. Those are the numbers. So you can see that you have 784 pixels, 28 by 28. So each one of those is going to be a predictor in X in a covariate matrix. So you have all these predictors for each one of the observations, and we also have the label. So we're going to use this. We're going to use data to train an algorithm. That's what we're going to do. So here we'll get to this later, but it's in the data. It's in the Labs package. You can get that data sets by using this function. It's too big to include in the package, so there's a function that downloads it. So what it has is it has a matrix of predictors and then the labels for the digits. Right, so that's what we're gonna show you that we can get up to, like, by the end of the lecture, we should be able to write our code, not even 20 lines of code, that will give you 95% accuracy for predicting what digit it is, just from the image, without you looking at it, honestly. Okay, so let's start with so I'm going to start with terminology that could be confusing to us statisticians if you never have seen machine learning literature before. So outcome is the same, that one's fine. That's what we want to predict. Then the features are what we would call covariates or predictors sometimes. That's all it is. There's nothing special about them. It's just that what they call them in machine learning. So in the MNIST data, we have 784 features. Then algorithm is another word you use that's sometimes confusing. So for statisticians, often algorithm is the actual code that does what you want done, like find the MLE. There's like code that finds it. And machine learning, they're a little bit more broad with the use of algorithm. So linear regression would be called an algorithm because it's a tool that can be used to make predictions, trained and make predictions. So they use algorithm in general. You'll see like machine learning algorithms. It's not just the code, it's also the idea of how you do. Training is the other word that we use a lot in machine learning. So train the algorithms. The algorithms tell us like ideas and a recipe for how to do it. But then you actually you get data like we have here with MNIST. We're going to train the algorithms on that data so that we can produce. And then here's another one that could be confusing, a model. So in machine learning, when they say a model, they actually mean the thing that actually works will make the predictions. So it's not like writing down a statistical model on the board. It's the actual thing that you use to make the predictions. Again, that we're going to build models is often what is said. Okay, so stop me if you have any questions. Also, if you have any other like things you've heard and find confusing, go. This is the time to ask, right? That's what we're here for, is to try to get you to be able to speak the language of machine learning, also do a little bit of it. Okay, so two types of problems that divide some of the algorithms that we learn. So there's categorical outcomes and continuous outcomes. So categorical outcomes, examples are MNIST data, the digits. There's 10 categories, 0, 1, 2, up to 9. And then there are other examples are the medical diagnostic tools. The most common one we'll be facing here, like for example, detecting cancer for cell-free DNA, circulating DNA. But there's a bunch of other ones that you might use, spam detectors. You use it all every day. Your email is about maybe 50 times more than you actually see, because there's a spam detector protecting you from a bunch of garbage. That's a machine learning algorithm, and it's categorical spam or not spam. Then there's a zip code reader is the example we're going to be using here. This is another example. You could consider Siri to be a machine learning algorithm that's categorical, where the categories here are many, because it's the phrase. It's like what you said. That could be millions of different things, but they're still categories. All right, so continuous is the other type of outcome. And those are, in machine learning examples, would be stock prices. So there's machine learning algorithms. They're not great, but they try to predict future price of a stock. Real estate prices, that one you might have used. Zillow uses machine learning to predict the prices of homes. Temperature, next week, that's another outcome. It's continuous. And then student performance, so it's now being used in education. The performance in a test. All right, notation. This is very similar to what we use, like say in regression. So yi is the outcome. If it's categorical or continuous, we still use the same yi. And then the features, just like in regression, we use x with the I for the observation, and then the second one, 1 through p, for the different features. So in the case of the digits, you would have one. You have, for every image I, you have 784 x's, one for each pixel. And then if you read papers or advanced books, they're going to always use matrix notation. So you're going to see bold. I hope you can tell that's a bold X. Bold X is the entire, bold XI is the entire feature vector for one observation. And something that I still sometimes get confused when I'm reading. Just remember that they'll you see there's a transpose. Vectors are, if it's one-dimensional, it's almost always the case that we mathematically think of them as columns, just because the math becomes easier. So you can write, for example, xi transpose xi gives you the inner product of x with itself. It's the norm or whatever you want to call it. Okay, so that's sometimes gets confusing, but yeah, that's, even though it's a row in our matrix, when it's just that one row in the book and the math, they think of it as a column vector. That's something that R does automatically. I don't know if you've noticed this, but if you type like, if you turn a vector into a matrix, it turns it into a column vector. It's the standard thing we do in math. Okay, so all right, more notation. In books that talk about this statistically, they often have it without the indices because these are random variables. So you can think of you just take a random digit that was written by somebody, or that's going to be the y is it's which digit it is. It's a random variable, and the predictor space thing can be thought of as random as well. It's how you write might be random, or who wrote it is a random selection. So that's very similar to what we use in standard statistical theory textbooks. Okay. All right. So what we're trying to do in machine learning in general is come up with a function of the predictors that gives us a prediction. So we often use f when it's a probability. Get to that in a sec. Soon we use p, but there it is. It's f of all the predictors. You're trying to build that f so that it gives you back a prediction. So we write it like dot y hat because it's a prediction of, and it's a function of the feature. So it's written like this. But this is what machine algorithms try to do, is use data to come up with an f. Yeah. All right, so we're going to learn, there's hundreds of ways of making that f using data, and we're going to just see a few of those. All right, so what is the challenge? So we get, in the future, when we sell our machine to the zip code reading to the post office, they're going to give it an image that's going to be 784 X's, and they don't know. The machine is just reading digits and sending letters to wherever, so we don't know the outcome. That's the challenge, and what we're going to do is we get data where we know we have a bunch of data, and we're going to try to build an algorithm that fills out those questions. So a little bit more terminology. In when the data is continuous, sometimes you'll see it called prediction. Sometimes it's called prediction no matter what. But that's more common for continuous variables. And then you use they have terms like the actual outcome y, and then which is what we actually end up observing, and then the prediction y hat. And then the error, which we'll say more later, is the difference between, for continuous data, between what you predict and what you actually saw. The categorical data, they often call it classification instead of prediction. And here we're gonna, usually what happens is you build, the final F is actually based on a decision rule, which is based on F for each category. We'll have one based on the prediction, and you pick, usually the way it works is you get back an F at K, and you pick the K with the highest F, and that gives you the prediction. And in that case, Y will be 1K. It'll be one of the Ks. And then the error is it right or wrong? There's no numbers anymore. You either got it right or you didn't. Now that turns out to be in binary data, that actually is 1 minus that is right or wrong. You either get, if it's 0 or 1, that gives you 0 means you got it right, 1 means you got it. Okay, so that's the end of the terminology. I don't know if anybody has questions, or there's terminology you've heard that you don't know what it is and you want to know. You can ask now. Questions? Okay. All right. So next, now we're gonna spend some time on a very important topic. There's a lot of confusion about this even among people who consider themselves machine learning experts, and it's evaluation metrics. So in statistics, we often are we're confident in what we're doing because there's statistical theory that tells us that certain choices, like say the MLE and the standard error of MLE, and adding two standard errors to the right and to the left of an estimate gives you a 95% confidence interval. That's the best the smallest confidence interval you can form that has the property of being 95% confident of it landing on the truth. Those are all based on theory. And if the model is right, then we feel like the theoretical asymptotics hold, we feel pretty comfortable that what statements we're making are useful. But with machine learning, it's very rare that we have theory that tells us all these things. So about the way we evaluate the algorithms is not based on proving some theorem about this estimate being the best in some way. We do things very different. We use things like we're trying to estimate MSE, but it's in a very data-driven way. So I'm gonna use a really simple example. It says it's really not a hard problem or interesting problem, but only just to show you the ideas of how these metrics work. So we're gonna go very slow here, and then once we get so we have the general idea, then we'll accelerate a little bit. So here, if you want to follow along, here, this guy. So there's this data set that has heights, self-reported heights and self-reported sex for something like 1,000 students and classes that I've taught. And what we want to do, just as an example, is we want to predict sex based on height. So the only things we have, and that's what we're going to try to do. Okay, so how do we evaluate this? So the general idea, and we'll say a little more later, is at the end of the day, we're trying to estimate the error of our predictions. And pretty much every approach is going to split the data into a training set and a test set. And the idea is that we're trying to imitate the situation that is the reality that's going to our algorithm is going to face in the near future. When we're done with our task, we're going to hand over our code to our collaborator or to a company or something that's out of our control, and they're going to try to predict on a data set that we have not seen. So what we're trying to do is imitate that situation. And later we're going to talk a little bit about overtraining and how that can affect how your optimism about your algorithm. The general idea is that you imitate that situation by dividing the data into two. So the caret package has this very nice function. And now I'm starting to use caret. That's how you can see it up there. Okay, so it's called the function is called create data partition, and you might ask, well, why don't you just make an index and split it? It's not that big a deal. Why do you need to split a special function? So there's several things that create partition does that it is nice, but one important one is that it tries to keep your test set balanced in the way that the training set is balanced. So suppose you have, this is important in many of our applications. Suppose you have a data set where you have cases and controls, but the cases are very rare. You don't want to have a situation where you split the data and your test that has no cases. You don't want that to happen because then it's like you can't test it. So this function by default makes sure that balance stays about right. You can read the help file. It does a lot. Well, that's one of the things it does. Here it's not going to happen. There's plenty of emails and mails that it won't happen, but just so you know that that's an important feature of that. So that once we have the training index using create, so that's just an index. Now we can create a test set, a training set, and a test set, and everything we do in terms of building an algorithm is going to happen on the training set, and then check out how it works on the test set. So that's how, instead of theory that tells us you did the right thing, that's what we do in machine learning. We say we tried it on a train, and look how well we did in the test. Okay, so here's some examples. If we take, what do you think is going to happen if I just guess? Right, this is just guessing. Right, I'm just picking at random between male and female. What do you think the accuracy accuracy is going to be. Here's my accuracy. Right, so that's everybody know what I sometimes assume that obvious, but maybe it isn't. This is accuracy. Right, so I'm saying this is my vector of predictions. This is my actual outcomes. This is a vector of logicals. If it's the same, it's true. And then the mean of trues and false tells you what proportion are true. That's what proportion are correct. That's why that works. So what, anybody want to tell me what that's going to be? I just guess by email or mail. 50-50, right? So 48, you missed by 50%. Not a surprise. Okay, so of course we can do better because on average, males are slightly taller than females. So here's not a very smart thing we could do. Let's say let's build a confidence interval for males, and then if it's more than 2 standard deviations away from the mean, then we call female. That's the algorithm. That one has a 77. That goes up to 78%. Okay, so all right, that is super not interesting or difficult. Now here's where we start getting into the ideas of machine learning. Now we picked that cutoff 2 standard deviations away from the mean, but that gets you pretty close to the mean height of female. So that's maybe not the best cutoff. Right, so we can now pick a cutoff that improves our accuracy. And all I'm doing in this little piece of code is I am going through from 61 inches to 70 inches and seeing what my accuracy is in my training set. Okay, that's all I did. I'm going to make a little picture. Looks like that. So if I put the cutoff at 64, that's where my accuracy is best. It's 83%. The cutoff to 64. Now that was on the training set. Now I have to actually see if it worked on the test set, and that's what this is. Once I pick the cutoff, the best one, now I have my accuracy in the test set. So this is as simple as it gets in terms of machine learning algorithm. We had training data, we optimized something. Then when we're done optimizing it, we check on our test set how it works. Not interesting, I know, but that's the basic. All right, now this example, I'm gonna have a little aside because this example gives us an insight into an issue with machine learning that's actually important to know, very important to know. So I want you to look at this, and here's where thinking a statistician can help. The cutoff is 64 inches. So if you're taller than 64, it's called male. If it's less than 64, female. 64 or less. So that's 64 is the average height of females. So that doesn't seem right. Like, why is that? That doesn't seem like a right cutoff. So you're saying if you're the average height female, you get called a male, and somehow we get a super high accuracy. Okay, so that's weird. All right, so now we're gonna move on away from accuracy and start talking about other evaluations, particular specificity and sensitivity. The simplest way to see that is as a 2x2 table, which in machine learning is called a confusion matrix. Much better name actually than 2x2 table. Okay, so the confusion matrix, there's a caret function that does that, but that's what I'm showing here is just the table output of it. That's the same as table in R. The function table in R will give you this. So look at that and tell me if you see what the problem is. How are we using a cutoff doesn't make that much sense. 60, so average female gets called a male. Somehow, like, we still have a super high accuracy. What's going on? This is the things you learn as a statistician should help in epidemiology. So the 2x2 table, the confusion matrix shows the problem. So, go ahead.
Predicting male, but not.
Yes, exactly. It's great at predicting male. It's terrible at predicting female. But what else? There's one more thing you're missing to tell why you get so good accuracy. There's more male. So this is another way of saying what you just said. Sensitivity is terrible. Specificity is great. And now what's a positive and a negative here? So the function confusion matrix takes the first, it takes factors. It's a very quick, so it takes factors as the data and the reference. These have to be factors. And the first level of the factor will be a positive. So now once you have a positive, females comes before male, F comes before M. Female is 1, male is 0. So sensitivity is predicting a female when it actually is a female, and specificity is. So that's why you can make the connection. And the problem is that the prevalence is very low. So we have great accuracy, low prevalence, but we have this problem. So this is, by the way, I don't know if you've been following along, but the CM function has been giving me all this stuff. So let me just show you that real quick. You just run this. I gotta go one more. This one. Whoops. One more. All right. So now I'm gonna make the fusion matrix so you can see all the fun stuff it has. It does everything for you. Okay, so watch this. 2 table, accuracy. Somehow it gets a 95% confidence interval. And then it has specificity, sensitivity, plus PPV and PV, prevalence, detection rate. And then at the end it tells you, oh, by the way, positive is P. So you know what all these things mean. Now the other thing it does, we might see this later, the digits maybe, but what if you have many categories? Then you can go one by one, making each one the positive, and then you get all these things for each of the classes. I think it might do that automatically when it has more than one class. All right, so very, very useful function because it just does it all for you. All right, where am I here? All right, so that's this is what we just did here is a very common problem with machine learning, that if your training set has some kind of bias, then your built model will have it too. There's a lot of talk about this. This is a really simple one, but it's not very hard to detect. But there are some that are hard to detect. That there's some bias, and you don't know if there's. So there's a whole area of research in machine learning dedicated to making sure that the algorithms being built are fair. Or in another way to think about it is just thinking: is it going to work out in the wild where the test set is maybe different than the trainings? Okay, so there's just a reminder. FP101 should remember all these things. So when we assess machine learning algorithms, when it's categorical, we do want to do both. Now, machine learning literature has 2 specificities. There's the true negative rate, like the probability of predicting a 0 when it is a 0. But they also use something called precision, which is what statisticians and epidemiologists call PPV, which is the probability of calling a 1, of it being a 1 when you call it. They use both. Actually, it's very common. I'm going to show you that later. Precision instead of true negative rate. All right. So I just did that. Okay. So one way to solve this, if you have to, just very briefly, if you need to optimize the algorithm, and you have you can't do specificity and sensitivity because you have to optimize it to something. Right? Just one number. to have the maximum. So there's things you can do like balanced accuracy or F1 score. So this is the average of precision and recall. Right, that's what balanced accuracy is. It's not a harmonic average because they're rates. When you have rates, what an average looks like. You might see it defined like this, but this is where it comes from. It's a harmonic average of sensitivity and specificity. So you can also weigh it by how important the two types of errors are. So another thing that's important to know in machine learning is sometimes the sensitivity is more important than specificity. So two examples are, is a plane going to crash? You absolutely want to have sensitivity there. Specificity is not that important, right? So you wait a couple of hours while they check the whatever engine they have to check. That's not as bad as the other one. So one of the errors is much worse than the other. And then in something like the death penalty, it's the other way around. You don't want to have a false positive. Okay, so there, if you have a way to weight, if you think you can weigh, you can take an average, a weighted average of the two if you want to do that. That's something you can do instead. So here's very quickly, I'm not going to run the code, but if you use the balanced accuracy instead of, so this is a function in caret, F1 score, then it picks 66 as the cutoff, which is makes more sense. That's right in the middle of the mean heights for males and females. And then you get better balance of sensitivity and specificity. All right, one last thing in evaluation metrics, ROC curves. The C doesn't stand for curve. What is it? Receiver characteristic curves. So ROC curves are really great for machine learning because it actually, you can now test your algorithm at different levels of both accuracies and precision, and you can compare algorithms to see how they do at different areas. So this is a way you can plot a ROC curve. So these are my two algorithms. The randomly picked, and then this is the probability of picking a male, the number you see there. And then this is the cutoff height. Okay, so you see that 66 is about where it gets balanced. And you can see that the picking by height does always beat the random surprise. So that's what ROCs are very good for, is to compare algorithms by keeping the sensitivity fixed and specificity fixed. You can compare sensitivity and vice versa. Keeping sensitivity fixed, which one has better specificity? Because it's very common that you could have two algorithms that their defaults produce, the default might be here and here. Right, so you say, oh, this one has better sensitivity. Yeah, but it has much worse one. So you want to be able to compare fairly. Then in machine learning, it's more common to make precision recall. So instead of they put recall is sensitivity, it's the same thing. And precision is PPV. So here, the advantage of using precision instead of false negative rates is that it does take prevalence into account. It'll go here, if you have males in one, then the prevalence higher, so you have better precision. Defined as a one, the curve changes. With the ROC curve, it doesn't change no matter what 0, 1. That you'll see in machine learning papers is much more common to show. But it's the same. It's sensitivity and specificity. Although in this one they put sensitivity here and specificity here. ROC curve the other way. All right. So another reminder, important that you learn in EPI 101. Prevalence is very important to keep in mind, especially in clinical applications. That you can have really good accuracy, very good specificity and sensitivity. So for example, if you're giving a data set where they say, I want you to build an algorithm that predicts a disease, and they give you a data set where half the people have the disease and half don't. So you build your algorithm and you get 99% sensitivity and specificity. You go really excited to the clinician, and they're like, "Oh, that's terrible," because it turns out that the disease is super rare. So even with sensitivity specificity of 0.99, the precision will be really terrible. It's such a rare disease. So you really need to make the specificity way high to be useful in practice. Right, so that's just Bayes' rule up there. That's just connecting. You can later look at it if you want for time with connecting specificity, sensitivity, and precision when prevalence, where's prevalence here, is in the equation. All right. So here's the curve. This is the specificity of 99%, sensitivity of 99%. This is your precision as the prevalence gets smaller and smaller and smaller. You can go all the way down to 0. It's very rare. But just something that might happen to you if you're working on a clinical application. You don't realize how good your specificity has to be for it to be useful. You have to be sure of that. Because it's a rare disease, it has to be really, specificity has to be really high. All right. All right, ready to move on? So now we're gonna get into more of the math part of how we evaluate this a little bit. All right, so this is MSE, just like in stats. We have a prediction and then the real outcome. Now I'm thinking of it as random variables. So it's good. It's a good tool to think as a statistician. You have one data set, but it was randomly taken from some. So it could have been different. So if you do the experiment again, you get a different prediction, your outcome is different. So this makes sense. This means you can do it over and over again. In theory, you could get a new sample and build your algorithm. So that is straight up MSE, your prediction, your outcome, and that's the standard metric that is used. So there are some that use absolute value, and then that produces algorithms like lasso and other things like that. And I'm gonna not go into that today. I'm gonna stick to square, the most common one. So that's what we want to find. The algorithm that has the best MSE is the one we're going to pick. Now that is super easy to say, but super hard to actually get. This is very hard to get. Like I said earlier, in statistical theory, we write models and we can actually get a pretty good idea what that is mathematically with, like, say, the MLE. But in machine learning, it's not MLE. Sometimes some of these things are really complicated algorithms that do all kinds of crazy stuff. There's no way of estimating this theoretically. No way. So you have to find some other way of doing it. The ones we've done up to now are not hard, but we're going to get to some harder. So notice that if it's binary, like some of the examples we were giving, where this is then this still works. Like a 0 means you got it right, and 1 means you got it wrong, and this is the probability of getting it right. So it's accuracy. It still works with binary data, that formula. Okay, so this is what we can use. The first thing that comes to mind is I train my algorithm and I get y hat, and now I got yi hat, and now on the test set I can compute this. So on my test set, I have a bunch of data. I kept like half of it, so I can compute this on my test data. And that is an estimate of MS. The observed, what they call it in machine learning, they call it the apparent error. What they call it. The apparent error is you have your test set and you test it. Now, this is the problem. I don't know if you can get rid of that sign. Yeah. It's a random variable. So that means that if you just use that, the variability that this thing has can lead you to make mistakes. All right, so we're gonna learn how to estimate MSE in better ways than just that. So another thing to point out, you'll see often the root mean squared error. When you're talking about it, when you're thinking about it, it's better to use root mean squared error, just like it's better to use standard error than variance, because it's in the units of what you care about. If you take the square root of MSE, now you're in the units of whatever it is you're looking at. So if it's categorical, it doesn't matter, but if it's continuous, it does. So if you have prices, house prices, the root mean square error will be in dollars, while MSE is in dollars squared, which doesn't mean it. Okay, so resampling methods are what we use to estimate this. I'm gonna go through a few of them. All right, so we're gonna get closer and closer to the real challenge at the end. But we're gonna take one step from the super easy height and sex to a slightly harder things with digits, but not quite at the digits yet. We'll get there. But this is to be easier to explain things. We're gonna get to the digits at the end. So this is a simplified version of the digits problem. Instead of trying to do all 10, we're just gonna do 2 of them, 2 or 7. And we're only gonna use 2 predictors. Why 2? Because I wanna make plots. I can make plots with 2 dimensions, but not 4. So that's why. Otherwise, we could use 4 and we actually can do pretty well. We're gonna use 2. And the two predictors are just very simple. We're gonna split up the quadrants we're going to split it into quadrants, and we're going to keep the number of the proportion of black in each quadrant. That's my prediction. So I could use all 4, and with all 4, I can do pretty well at predicting 2s or 7. Because the 7 is it's going to be like, you can have 3, while the 2 could have these other 3. But I'm going to, just for simple exposition, I'm going to do 2. I'm going to do this quadrant and this quadrant. That's it. This is a start. Be patient. We'll get to the more interesting stuff. So what is that? What am I showing you here? This is the largest X1. This is the digit with the most black ink in the first quadrant. This of the 2s and 7s. Okay. This is the smallest. There's no ink. That's 0. No ink. That's X1 is 0. X1 here is high. This is the second quad. This is the second quad at the bottom. This person used like a magic marker to write the digit, like really thick. There's a lot of black here. And this is the smallest lower quad, right? But just a little bit of ink there. So that's what I'm using. This one and this one, just for now. So can I predict 2 or 7 with just those 2 quadrants? That's what I just said. Right? So I have yi is 1 if it's a 7 and 2 if it's a 2. No. I think I have it. 1 is 7, 0 is 2. I forgot to mention this. When the data is binary, it's common to have to use the label 0 and 1 because the math for the MSE works. So it's very convenient mathematically. When you have more than 2 outcomes, then you can't do that. But you do kind of do it sometimes because when you have more than one category, often the machine learning algorithms are gonna do 1 by 1. Is it a 0 or not? Is it a 1 or not? Is it a 2 or not? Is it a 3 or not? Well, we'll get to that. But this is my feature now, it's just 2. Okay, so there's my data. 7s, right? Those are the blues. This is why I chose 2 because I can make a picture. And 1 and 2 are the red. You can already see we're gonna probably be okay. We're gonna do okay predicting. Like 2 is here, 7's out there. Right? You can kind of see that we're gonna do pretty well. Okay, so now let's do it. Let's build an algorithm. So here is the truth. This is an example I made. So I get to see, you never get to see this in practice, but here for teaching, we get to see it. This is the true probability of being a 7 as a function of x. So if you're here, you're almost guaranteed to be a 2. If you're here, they're pretty much guaranteed to be a 7, right? So 7s are here, 2s are here, and then there's a not sure. Right? So here it's 50-50, 2 or a 7. So that is the probability of being a 7 given x1 and x2. Okay, so now let's pause and think about our real example. In our real example, we have not 2, 784. So you can't make a picture, but you, as statisticians, as mathematicians, we can kind of make a picture in our head. There's a 784 dimensional space, and any point in that space will have a probability of being a 0, 1, 2, 3, 4, 5, 6, 7. Right? That's like that. I want you to be extending this to real machine learning application. That's why this one you can see in a picture. The other one you can see only in your abstractions in your mind. But there it is. Now this is question.
Just making sure I knew the axis meant. X1 is the rate of ink in the top quadrant. Yeah.
Okay, so what this is saying is, if you have a lot of ink in your top quadrant, you're pretty much guaranteed to be a 7. Now that's not true for the bottom quadrant, because if you have too little or too much, you're probably a 7. If you have just about the right amount, then you're a 2. So the other thing I want you to notice here is that's already a pretty complicated function. Like what is that? That's not a plane. That's not a sinusoid or cosine. It's not an exponential. We don't have a parametric function for that really. It's not a quadratic. It is close, but not quite. So that's why machine learning is a whole different complicated field, because reality, the world, is not nice to us in that sense. It doesn't say, ah, here you go, it's just a parabola, or it's just regression is going to work, or it's a sine wave. It's something else, complicated thing with interactions and all non-linearities, and we have to somehow get to it. So this is just 2 dimensions. Now again, think about 784. Okay, so this is where this is the truth. This is, oh, sorry, the black line. Thanks for asking. I didn't say that's where it's a half. That's the border. So if you're inside the black, you're more likely to be a 2. If you're outside, you're more likely to be a 7.
Based on the whole training piece.
That's basically what I did. I took the whole 60,000 and I did like a very small. I could also simulate it, but I thought it'd be better to have like a real data set. Okay, any other questions? Okay, so this is P of X. Let me say it as statisticians. The probability of Y being equal to 7 given X1 and X2. That's what that is. It's conditional probability. I want to estimate that. How do I do it? Well, this is what they teach you in like Stats 101 or maybe grad school Stats 101. That's all we learn, really, I think. I don't know if you learn other stuff, but that's one thing you learn. Logistic regression, right? So the probability of X, you take the logistic function and it's a sum of, that's one thing we know. So that's what we're going to try first, because that's all we know. So that, once you fit this, and here you can use MLE, you get your betas. Once you have your betas, you can get a p-hat. You can do machine learning. Right? You can say my machine learning algorithm says if I'm going to predict a 7, if my estimated probability is bigger than a half, right? That's machine learning. You will see papers that claim to be using machine learning, and it's this. It's literally logistic regression. So there's your accuracy. You do that on the test set. 77%. Not better than a half, but can we do better? We definitely will be able to do better, in part because logistic regression, the boundary, just to give you a sense of why it's going to fail. This is where it's a half, right? This is the boundary. You're with me, right? When this is 0, it means P is a half. When P is a half, logistic of half is 0. something special here. That's the border. When this happens, I'm on the border. It's Px is a half. That implies that x2, so that border, that border is a function x. You can write it as a function of x2 as a function of x1. It's a line. You see that's a line? But we have no logistic regression cannot do anything about that. It has to be a line. Has to. There's no way around it. So that's the best you can do. That's not close to the actual function. So we, unfortunately, nature is complicated, and that's rarely a logistic regression that'll work. Okay, so let's now learn our first not so standard, not something you're learning in grad schools in stats for an algorithm for machine learning, and it's basically a bin smoother. You want to connect something you learned in some stat class. So what we're going to do as our first machine learning algorithm is we're going to take each x, any x, right? Remember, x is a two-dimensional point. You pick a point in the space, two-dimensional space, and I'm going to look at the 5, well, k. The 5 is the default, so that's why I say 5 in the code, in the algorithm. The 5 nearest training set points, and I'm going to say, are those 2s or 7s? They're going to vote, and the winner gets it. So if there's 3 7s and 2 2s, I'm voting 7. Okay? And you can estimate P too. You can just say the proportion of 7s is my estimate of P. So if it's 3 and 2, my estimate is 3/5, 60%. I can do that too. So I go, and that algorithm is easy. Just go all the x's, find that P, and here's how you run it. In caret, there's this function called kn3, not to be confused with kn2 or kn1. And it runs just like GLM or LM, right? Dot means use all the predictors. Y is the outcome. It's my train data, and then the default is 5 neighbors. Then I'm going to predict the test set. Predict. So this function has a predict that goes with it. And I say type class, because right now I just want to get 2 or 7. I don't want the probability right now. And I already beat GLM. Just off the bat, just with the default. Why do I beat it? Because it's more like this. It's more flexible. Now this is the estimate of P, which takes the 5 and it computes the probability based on that, right? on the proportion of set. So there's only 6 colors here. It's either 0, 1/5, 2/5, 3/5, 4/5, 5. Okay, but that's good. That's better. I think it's better, but there's an issue. What's the issue with that? I mean, even if you didn't know this, it just seems weird that there's this little like bays and islands and right. That doesn't make sense. Right? There's like thing there and that guy over there on its own. So that's overtrained. So you can see it. So it's shaping itself too much to the training set. By chance, there happened to be 5 7s or 3 7s too close to here, and it just got blue. So that was because it's 5. If I get another sample, it doesn't happen. So that's probably gonna be errors. So here it is. You can see it. 85% on the training. I'm predicting on the training, I get 85, and on the test, I get 81. So it looks like I overtrained them. This is a little bit higher. It's the evidence that we're overtraining. And then we're going to get to something more formal. This is just to give you ideas. Now this is the most overtraining you can do. K equals 1. So you predict with the closest one, which is you. You get perfect. in the test, in the training set. It's not perfect. You know why it's not perfect? There's one example where there's one point that's in the same place, and there's 2 points in the same x1 and x2 that it's a 2 and a 7. So that one's wrong. But in general, if that doesn't happen, if every x is unique, it'll be perfect. You're predicting with yourself, so you have to be right. Now we go to the test set, and it's terrible. It's almost as bad as regression. It's not as bad as regression, but it's close to that. So that's a big difference. That's because we overtrain, and that is why we have to keep ourselves honest. We can't trust that we can't say, "Oh, our algorithm's great," because it's overtrained. It trained to the data we had, and once we go to the real world, we will not do as well. So here's what you can see it happening. So anytime there's a blue guy in there, it just gets a little blue around it. Those are all the regions that are closest to that point. But then then there's a red one in there, so it's an error. That's the extreme overtraining. And so here you see anything here is going to be red because the closest thing is a red. All right, so what about making it bigger? So if we make it too big, this is 401. I just picked a big number. So now it's the 401 closest neighbors. Now you get basically regression here. It's too small. So it looks almost like this. Now, because I'm basically fitting a plane. There's so many points. So how do I pick? So that's it. That's maybe more than half the battle of machine learning. One half the battle is picking the algorithm, the other half is tuning it. We use the word tuning it because we call whatever parameter makes the algorithm different, it's called the tuning parameter. So now we can go back to terminology. We have an algorithm, k nearest neighbors. It has a tuning parameter, k. We have to train the model. We have to pick a k with our data. And also, once we've picked that k, then actually build the predictions. Once we have that, we have a model. Now the model we can give to the postal service. All right, but now how do we pick k? So one approach, it's not great, but very quick, is what I just did. You know how I was training and testing with different k's? I just do it. For every k, from 0 to 250, there is the blue is the red is what I'm looking at. The red is what I'm going to use to choose. The blue is the training set. I'm including that so you can see how the overtraining works. It's way overtrained with 3. I think that's 3. Right? But then as you move bigger k's, you get a little closer. Now, what do I pick? It's this one, that one. That is a random variable. That is MSE hat. This red one is MSE hat. It's unbiased, but it's a random variable. So it's not a great approach. But it's okay, it's something. It's better than nothing. So I could just use that. But we're gonna do something better. So 2 problems with that with the apparent MSE. One is it's a bit random variable, so it moves too much. So it's not a very precise estimate of the actual MSE. But there's another subtle thing here. If we pick the k based on our test, when we go to the real world, we're not going to do as well because we pick the k on the test set and we evaluate it on the test set. You see what I'm saying? We fit the model in the training set. But if we say, let's use this one because it has the best k in the test set, we use the test set. can't use the test set. So we need those are the two problems with MSC, with this MSC. So we're going to change that, and we're going to start with, I'm going to give you a little bit of the math motivation for cross-validation. So here's what we want, here's what we did. This is what we showed you. The red line is this. The MSE for a given lambda, I'm introducing new notation, right? Every lambda gives me a different MSE, is the predictor with that lambda. This is now in the test set, right? I get the model from the training set for the Y, and now I'm gonna evaluate the MSE. That is a noisy random variable. It's all we have right now. So what do I want to do? If I had, in a theoretical world where machine learning would be easier, I could just say, all right, let's give me, you know how you just spent 2 years having people write numbers and taking pictures of it? Can you do it 1,000 times again? Right, so I go to, what's his name? Guy who did this? Jan LeCun. Hey, Jan, can you do it 1,000 times more? Obviously, he's going to say no, but let's suppose he said, all right, I'll get back to you in 100 years. Now I can do it 1,000 times. I can do it again and again and again and again, and I can get a much better estimate of the MSE. Right? And the law of large numbers tells me that as B goes to infinity, this goes to the MSE. Right? So you see what I'm doing now? Every B is a whole nother MNIST data set. And that will give me a good MSE if B is big. Now that's theoretical. It's not realistic. So instead, what we're going to do is, first, I'm going to show you cross-validation. Is we're going to do the following. So we already did this. But now, to avoid this problem of picking the K on the test, we're going to keep this test, put it away, don't touch it, and I'm going to create a training set and a validation set. This is where I'm going to pick the K. Train the model for each K, pick the best K, then test. Now that's one. So what can I do to imitate the situation that we just talked about? Well, I can do it. I can do that 5 times, 10 times, some number of times. That's cross-validation. I mean, it's better to see it with pictures. So what I'm going to do is I'm going to divide it. I'm going to split it 5. In this case, I'm doing 5. Right? So I split it 5 times. In this case, I'm not doing completely randomly. I'm making sure that every observation appears once in the validation test. That's the most standard way of doing K-fold cross-validation. So in each one of these, I will get a MSE estimate, and then I'll take the average of those 5. Why 5? 10 is another choice. The reason is because it takes a long time. Right? So that's usually what people use, 10, 5. So you don't get a super great estimate, but it's better than just 1. Much better than this. Okay, so you get the idea? So I take my train and I split it 5 times, keeping the validation so that the validation tests all of them together are the whole data set, and then I'm going to take the average at the end. So then I do this. This is 5. So we already did this once. We do it again 5 times. I get an average, and now it's a little bit better estimate of that. So you divided 80-20 5 times, and 90-10 10 times, 95-5 20 times. Now it's getting a little slow. But that's the idea, cross-validation.
The same test set for all of those roles.
The final test, I haven't even gotten there yet, right? I'm picking the lambda. Then we test, right? There's the validation gives me this. This hasn't been touched yet. Now at the end, I test. So that's my last frontier. That's right. And that one, now you can say, well, that was random. Yes, that one's random too. So we could do that 5 times But that's now whatever time it took to do it, that what I just said, which took me a lot, now it's 5, now it takes 5. So that's the reality of the game, and that's how we usually. Okay. So then one last thing in practice, at least when I'm doing it, once I'm done, once I have lambda, once I pick my tuning parameter, and I know it worked, and I checked on the test set, I just fit the whole thing on the whole data set to see how it works. And now that model gets deployed to the field. Okay, what I'm saying, look, so I'm done. I say, okay, lambda, the best lambda is 13. And I'm going to fit K and N with 13 for the entire data set. And that's what I'm sending out. Because I already know 13 is a good choice. All right. And when I report and when I predict my MSE, it's the one I get from here. And if I had time, I would have done it many times and I would have taken the average of those. Okay, just want to be very clear in each. Here I'm doing, you take this training set and you split it into trains and validations, and you got your lambda there, test here, and here, and again, it's all. Okay, so one last point. The default procedure in Caret, and the favorite of many, is not to do cross-validation, but something else called bootstrap out-of-bag sampling. A very similar idea, but it's more flexible. You can do more, it's easier to do more samples. And the idea is like this. I hope you're familiar, it's bootstrap. If you're familiar with bootstrap, you'll know what's coming. You take your data set and you randomly pick 80% the size. So if your N is 10,000, you pick, I'm sorry, no, you pick 10,000 at random from your validation test with replacement. Right, so let me start again. You have your training set and your validation test. Your validation test is sorry. You have your training set. You don't make a validation test just yet. You have your training set. You pick with replacement some number. Okay, so now whatever doesn't get into the sample is your validation test. Because some are going to appear more than once. It happens by chance. But they're independent because you pick them at random. And then the ones that are left out are where you compute the MSE. That's the bootstrap, and then you do, and it's the same idea. That's the default in Caret. So here's final predictions. Here's the first one I showed you. That's just one. The accuracy. Then the green one is cross-validation with 10-fold. So I left 10% out 10 times. You can see it's better, but it's still a little variable. That's the green. And then the blue is bootstrap with 100 bootstraps. So I did 100, not 10, 100 times. I took a bootstrap sample and got the B was 100. And now that looks pretty smooth. That blue one looks pretty smooth. And you can see the maximum is somewhere around here. So with the green, you might make the mistake and pick this one, although it's not that far. It's gonna be okay. But the blue's the best one, obviously. Why not always do the blue? It's 10 times slower than the green. So that's a practical consideration that can be the difference between a year and a month. Right? That's sometimes it comes to that.
If you had done 100-fold,
it would have been centered, but it's okay. Any questions?
the size of your data set. So if you
Yeah,
have
I have
like
it,
1 million
yeah.
points versus
Yeah. How that? So let me say, but notice that the MSE, so the MSE has an N. So that makes it, so if you have a big data set, the MSE has less variance. But if your real function is has a lot of shapes and wiggly, and you're still have a lot of variance in that estimate, even if n is very big, if it has a lot of nooks and crannies, it's not a smooth function. And it's not, the variance is still pretty big for the, even when n is big, the MSE could have, that MSE could be quite better. Yeah,
This looks like something that works really well on a very big data set, right? I mean, but in general, clinical data sets are not.
what are you thinking? What number are you thinking?
No, I'm thinking, I don't know, 50 individuals, something like
50.
that. Like
Yeah, well-
100.
So with 50, 25-fold is okay, right?
It's okay, you think?
Yeah. So what you're one thing you're getting at, and I'm glad you asked because I forgot to mention it, is that when you have smaller data sets, when you do leave one out, then the data set now is different. That you're fitting the model. Because if you leave, let's suppose 50, and you leave 12 and a half out, right?
Yeah.
Now you have 38.
Starts getting.
So instead of 50, you have 38. So now K and N might not work as well anymore because it's 38 instead of 50. So there, when you have situations like that, then you have to be careful that you don't leave out too many that makes your algorithm be very different.
Yeah,
than how
because
it works.
within those 30-ish, you need to also
Yeah.
cut out the validation.
Yes, right. So then that in those cases, Bootstrap might be work better.
Yeah, sure, maybe that answer. So but they work anyways for it, like with, in theory, with each sample size, with each data set size. There are not restrictions on that side, right?
For what?
For cross-validating
I mean,
methods.
There's
even
no restrictions, but you start getting into problems of, in the case of going from 50 to 38, then there's a little bit of bias now because it's a different. Oh, it's a different. I'm sorry, it's a different. Yeah, it's a different sample. It's a very different sample size, where it matters because it's percent-wise. Yeah. But yeah, so Bootstrap will work better than now. I'm gonna give you the examples where you have to be careful with Bootstrap. I'll mention it because digits is one of them. K and N is one of them. I'll tell you that in a minute. Okay, so now I'm gonna just go through. So we're about to finish on time. So I'm gonna just go through a few examples of supervised learning methods. So you get a sense of things that are out there and show you how they work on this data set. So there's the optimal K and N. It's good. It's 50 something Ks. Pretty good, right? See why it works well. So there's a whole other class of models with small data sets. These could work well. They're called probabilistic classification models. Sometimes they used to be called generative models, but I think that now causes confusion. The reason they're called generative or probabilistic models because we're modeling the X now too. The other ones are called discriminant model methods, where you just model the conditional probability or conditional expectation. Here I'm modeling the joint distribution. I'm actually trying to model f of x given y. Okay, so notice that in the previous one, we did not do that. We just went after the probability of a 7 given x. We did not talk about the distribution of x. Now, the probabilistic classification I am doing, I'm saying, I'm going to model the probability of x given y. And that's very tempting because that gives me the optimal rule. Bayes' rule is called. This would be the optimal, if you could get these Fs, this is the optimal approach. There's nothing better you can than Bayes' rule. That's theoretical. That's it. Now, why don't we always use this then? Think about this for the digits. 784. That's the joint distribution of 784 variables to get, right? You're not going to get that. But if it's 2, like in our example, sure. Let's go for it. Let's try it. In our example, we have 2x. Not that common in machine learning, but there's some examples like that. So then I can make an attempt to do that. So here's our attempt. This one's called quadratic discriminant analysis. And what I'm saying is x1, sorry, the distribution of x, remember x is two-dimensional. The distribution of x for the label 7 is normal. This is the normal 95% critical region. But so what I'm saying is if I look at the 7s, the distribution of those blue points is bivariate. It's not that once you look at it a little closer, it's not super great, but it's okay. It's okay. The red ones definitely look okay. The red ones look bivariate normal. The blue ones are a little bit like they have a little bit of a shape, so it's not quite bivariate normal, but it's not that bad. But that's it. Now I'm done. I can get all this. I just need the means, two standard deviations, one correlation for the 7s, and then for the 2s, two means, two standard deviations, one correlation. That's 10 parameters. You can do it. And here's the solution. This is my final. That is a quadratic by definition. It has to be. It's not bad. It works well. You can see why it's going to work well because that fits the data pretty well. That's quadratic discriminant analysis. Now, that's two covariates and two labels, 10 variables, 10 parameters to estimate. Now think of 784, 10 labels, forget it. You're not even going to try. Now there's another issue that comes up when this is just two, but if you had, this could come up in clinical applications where you have 5, so maybe you can try it, 5. So now you're assuming that it's jointly normal, 5 things. The problem is, the problem's gonna come when you go and estimate the covariance matrix, because there's 5 choose 2 correlations. Now that's 10 choose 2. Yeah. 10, right? So now 10, and if you have several labels, that's 10 times the number of labels, so it gets to be too much. So for gene, this is used in gene expression often. So the first publication in Science that had this new algorithm for predicting cancer from gene expression, it was LDA. They published it as a new thing, but it was the 1920s algorithm. So with gene expression, you can imagine, so suppose you have 20 genes and you want to predict cancer or normal, you can maybe do it, right? You have your 20 genes, you have 20 means, 20 standard deviations, you can get that from the data. The correlations will be tricky, but what if you assume that the correlation is the same for every class, which isn't it could be the case with gene expression, for example. By the way, this is just showing you how this isn't a great, it's okay, but it's not a great fit. It has a little bit of a curve. That's unrelated to what I was saying. So LDA assumes the covariance is the same in each class. So that reduces by the number of classes the parameters you have to estimate. So it's less parameters. So now, not even notice, but now see how the ovals are before they were kind of like twisted, now they're in the same direction. By definition, I just said they have to have the same covariance structure. So they have to have the same correlation in red and blue.
It's not just correlation, it's also the variance. It looks like
No, it's only the correlation. Well, you could pick. Yeah, it is a variance. It is the variance too. It's the whole covariance matrix.
Yeah, it's all.
So the problem with that, if you do the math, is that the border is the line. Now, if you have more than one class, it's multiple lines. So LDA, the first Science published gene profile paper was LDA. They gave it some other name, but it was straight up LDA. Okay, so more classes, it extends to more classes, right? It's just Bayes rule. So now I just have K. I just have each class. It's just straight up Bayes. So those are good for small data sets. QDA, LDA. All right, other algorithm CART. I won't have time to explain it, but CART is also very interpretable. What it does is it goes predictor by predictor, trying to figure out if there's a place to split where it makes the two the split data have a entropy, so that you find a split so that the data is as they use the word pure as possible. So it's pure sevens or pure twos. So you try to find splits in X1 and X2 so you get that. And when you do that with CART, you can see it kind of works. And it gets in. And then if you randomly sample from the data with a bootstrap and you do CART 500 times, you get random forests. So random forest is an average of a bunch of CARTs. It's a forest because the T in CART stands for trees, so it's a random bunch of trees, so random forest. So that also looks pretty good. That one you can smooth random forest. You can make it more smoother by changing a parameter called null size, and that again looks pretty good. Okay, so the last half hour, we're gonna predict digits. Okay, any questions about these? Should I have let me see if I can find it. Wait. I'm gonna show you a animation that shows you really quick. Right, so this animation is this is a data set that has a trend. I'm trying to estimate it. You can see the points. So what the animation is showing you is each time it changes, see the trees, it's a cart. And the cart is this gray line. So you can see it's like a step function because it's just making a decision of where to split, make the data pure. So now the other thing you're seeing is every time there's a new tree, you see how the points change? That's because each time it's a different bootstrap sample. So you're taking your data, taking a bootstrap sample with replacement, fitting a cart to that, and then doing it a bunch of times. And so you can see that all the trees that have been built are like in dashed gray. And then the average of all the trees can be a little bit smaller. That's the final answer at the end. So
That's a random forest.
at the end, right? So you can see the blue is a random forest with 7 trees, 8 trees, 9 trees, 10 trees. As you get more and more trees, it gets to be smoother and smoother. So that's how you can get smoothness, even though the building blocks are these edgy things. Now this is 1 dimension. Now you have to imagine this in 784 dimensions. Okay, so let's build some models. All right. So we're gonna do this. This is the MNIST. It takes a little bit. Don't do it. Everybody does it at the same time. We're gonna crash the network because we'll have to fix it. So now I have the MNIST data. So you can see. Yeah, there's train and test. And then that's going to be a matrix, a list. Oh yeah. These are the predictors. Right, 60,000 digits, that's 784 pixels. And then you have the labels. Oh, no dim. Okay. So we can take one of those, for example, one of those images. Let's take the third one. Right, there it is. Those are the predictors. I can use 794. I can make it, if I make it into a matrix, 28 by 28, yeah, I should see it. Let's pick another one, not 3. Let's pick the 4th one. That should be a 0, so let's check. It should be a 0. Okay, there it is, 0. Oh, it's upside down. Yeah, yes, I can do 28 to 1. Okay, so now I'll pick another one, pick the 5th one. You see what I'm doing? I'm just showing you the totals. The other one? Yeah, it's a 4. So the 5th one should be a 4. Okay, so that's how we're gonna do it. Now, this is, don't be confused by the fact that this is a 28 by 28 matrix for one observation, but they're really just one long vector predictor, 780. I'm just showing you what the data matches the thing. Okay. So that's what we just did. So one thing I'm going to do is I'm going to take, I'm actually going to run some of these things. So I don't want to wait. So I'm going to take a smaller subset of 10,000. This is not cross-validation or any of that. This is just for the class. Because again, I want to finish in half an hour. So I'm going to run it on 10,000 digits instead of 60,000. So I'm going to take 10,000 train and 1,000 test. Okay, so now I have smaller data. Okay, so now we're getting into the like nitty-gritty. So we're going to use caret. I recommend matrices. If you can, if all your predictors are numbers, stick to matrices, don't make data frames. Caret work with data frames. Most machine learning algorithms in R work with data frames, but they're going to be slower. You just make everything matrices, things are faster. You also have to make, I already did it, you might have missed it, but I made the labels factors. Caret needs that. You give it, if you give caret 0 to 9, it's going to think it's the number 0 to 9, and it's going to do regression. It's going to use it as a continuous outcome. It's not going to work. And you won't know. You just get it. You just get the average of 0 and 1 is like some. It's not, it's not 1.5. No such thing. These are labels. Okay, so I turn them into factors. Okay, so you have to, if you're going to use matrices, you have to give them names. Why is that? Because when caret does something and says, I'm going to use these columns and then I'm going to go to the test set, it needs to be sure it's the same columns it's using. So it does check for the names in case the things got, in case the columns got like shifted. Right? It wants to know that that column has that name. So it's good that they do that. So avoid that error. So you see, I'm just giving them the same names because it's random names. I'm not random, but just 1 through 784, doesn't matter. Call it anything I want as long as they're unique. Okay, you get what I'm saying? So data frames by construction, the variables have names. If you don't give it names, it calls it V1 through V784. Matrices don't have that. You have to actually say, give it names. And now we're ready to run algorithms, I think. Okay. Okay, so one thing, if you're using caret, you want to have the manual handy, because these are all the algorithms you can use, a lot of them, and each one has its own things that you can optimize and names you have to use. So you have no choice but to be looking at the manual to figure things out. I'm going to maybe give you an example of that in a sec. Okay, so all right. Put the manual aside. Another important thing about caret. So in R, train, the function, I should have started with predict. The function predict is what's called a generic. It doesn't actually, it's not a function that just runs. Predict looks at what object you're training it, and then it figures out which function to run. So if you run LM and run predict, and then you run GLM and run predict, two different functions get run. It's very important to know that. So if you said the arguments all of a sudden change. So if you're using predict and you want to know what it's doing with a GLM object, you have to look at the help file for predict.glm. Otherwise, it's going to tell you it's a generic function. So that's annoying for machine learning because if you're trying different algorithms and everyone has its own predict, it's a nightmare. So one of the beauties of Caret is it just makes everything work together. It's great. It really is great. Because if you're testing out different things, your code doesn't change that much. So check it out. Here I'm training 3 models: GLM, QDA, quadratic discriminant, and KNN. Look at the code. It's the same. It's the same. I don't have to remember arguments, and that just works. So when I use predict, it just works. If I use predict, it has the same arguments. This is one that changes in predict. So why does predict have that type argument? When you use predict, you can either get the estimated probability or you can get the actual call. If it's a GLM type method, you could get the link function predictor or the transform predictor. So there's different things that can come out. The predict in Caret, that makes us so if you want raw, that's the actual call. You say raw. If you want probability, I think you say prob. You can look it up and what the help file will tell you. Right? So this is the predict for Caret. It's predict.train. I think it's the actual function. So now I can do things like this. Right? So now that I've trained these models, I can like run a sapply on those things and write the same exact code or fit, and it'll just work. And so here I'm comparing 3 methods and I see, oh, KN is the best. Okay, the other thing that the train did, and we didn't know, we didn't really see it, it actually runs a bootstrap cross validation and it picks the best K for us. However, what K is it to try? So if you want to learn that, you can do model lookup. And it says there's the parameters you can optimize are K. I can't forget, how do you get to see which values is it? Oh, here it is. It's not, I can't remember where it is, somewhere in here. But what's it trying? Somewhere, it's got to be somewhere in here. But it says it's going to try K, and it's going to try, I think the default for K is 1, there it is, 5, 7, and 9. If you just run train with no defaults, then you can actually call a ggplot on what comes out. That's a nice little feature. It'll plot accuracy versus the K. And you can see it tried 5, 7, and 9. Pick 9, that's the one that works best here. But if I want to do other ones, now I have to change, I want to change the 5, 7, and 9. So how do I do it? So there's an argument called TuneGrid. It's general, so it works for any of the algorithms, that same argument. You give it the choices you want to try out. And model lookup tells you what are the parameters you can optimize. Every algorithm will list, model lookup will tell you which are the parameters you get to optimize for that particular algorithm. So if I'm going to do 11, I got to change that. It's 1 through 11 to 105. I'm just going to try that instead. I can do this. So this is what you already saw up to here. Now I'm adding TuneGrid. Data frame. Now, how do I know use K? Because when I did model lookup, it told me parameter was K. I have to name it, and then I can tell it what to try. Whatever you want. This is 11 through 105, 4x4. Right now it runs. Let's run it. See how long it takes. It won't take that long. I bet you it doesn't take more than a minute. Maybe it does. Oh, there it goes. It's finished. Okay. Okay, so there it is. It ran. This is the best one. Now that's the one I'm going to use. So one of the nice things about the training carrot is that once it runs that and it has it has the accuracy for each K. If I call it, so here's the best one, 59. You can get it by best tune. The final model is the KNN with 59. That's if you're gonna use predict, you can use predict on that, and it'll have everything you need. But you don't usually do that because one of the nice things about predict, if I do predict train KNN, it'll take the best one. Right? So it's gonna predict with the best. Makes sense, right? So you don't have to actually go and find it, it just does it. So there it is, 82.5. So by the way, I haven't been using the real digits just yet. Right? This is the easy data set. Otherwise, that call would have taken 15 minutes. Okay. So what am I doing here? Okay, so now, so with KNN, something that I'm gonna explain it because it's a subtle thing that is good to know. Think about bootstrap with KNN when the K is small. It turns out that with all the digits, K nearest neighbors with like 3 or 5 works really well. You think about it, you find the five closest digits, they're gonna be good at voting what the actual thing is, because you have so many to pick from. Okay, that point aside, think about this. If you're using bootstrap with, say, K nearest neighbors 3, if you bootstrap, you are going to get the same observation more than once. It's going to happen, right? Because it's with replacement. So your nearest neighbors, if you're using 3 and you bootstrap and you actually, it can happen, you linear 3 times, you're going to be the nearest neighbors 3 times. So bootstrap isn't great for KNN with small k. It's one of the examples there. That's why we don't want to use it for here. So with K nearest neighbors with small k, you probably want to make sure that you use cross validation and not bootstrap. So I have to tell train not to use something else. And here's how you do it. TR control. These you're not gonna remember these. You have to just look at the manual, and I don't remember them. I always look them up. TR control, and where did I define control? I think in a previous page, or did I?
No, it's right there.
Huh?
Line 1.
Yeah,
Oh, thank you. So there's it. So I'm saying use method CV, not boot. Number 10. So this is 10-fold. Leave 10% out. That should we run this? Yeah, it's gonna take a little bit. Yeah, I'm not gonna run it, but I think it takes less than 10 minutes. But think about what it's doing. This is for the entire, oh no, this one is fine because this is for 27. It's for the other one, it takes long. Okay. All right, so that's how we use that. What I just taught you, you can fit now 200 different algorithms with what I've just taught you. That's all you need. Because Crowder has all that stuff. Now, there's one other important thing that I want to talk about for the last 10 minutes before I just show you the results at the end. And it's pre-processing. This is not talked about as much as it should. So there's a lot of things we can do to improve the algorithms. It's nothing very fancy. It's some of the things we do in our day-to-day when we're exploring data sets, taking out covariates because they're crap or they're outliers, all that kind of stuff. It helps a lot here. Log transformations, centering stuff, all that. You can do that in Caret. I'm going to show you one example of one of the things you can do. And it's removing predictors that don't do anything. So if I look at the standard deviation across all digits, okay, so for every predictor, I go across all digits and I compute a standard deviation. There are a bunch of digits that have no variance. To the corners. I don't have the plot. The corners, nobody writes in the corners. There's no variance. There's no point including those. There's nothing's happening there. Might as well take them out. All the action is in like these. It's just the middle ones. So there's a function in caret called ne0 that it just tells you which ones are not varying. And sorry to skip all this, but I just want to show you. I'm going to come back to this in a second. You can say to train pre-process, and then there's a list. You can look at the help file. That's one of them. That says take out all the predictors that have almost zero variable. Now, the reason you want to do it here and not on your own is because if you do it on the entire data set, you are now bleeding in information from the train to the test. It has to be done within the cross-validation. Right? If you do anything, if you use any information of the test set, you don't underestimate how that could screw you. So just never do it. Always train every single thing you do. Do it in the training set. And the function train, make sure you do that. You do it all in the cross, in the train, and then in the validation, it checks if it worked or not. So it removes features using the train, and then in the validation, whatever you decided to take out is taken out. It doesn't reuse the variance again. So that guarantees that it'll do it the right way. Putting it in here. Let me show you one more. So this is now the real thing. If you run this, it's the real thing. This is like all the digits. So look, I actually ran it before coming here, 95%. Just by KNN. And I think it picks 5. Okay, so another one that's very useful, PCA. So now I say pre-process, take out the crap. I don't actually could probably skip this because PCA will do it. This is saying do PCA first on the training set and keep. How do I say that? There's a default. So PCA, the default is keep enough PCs to explain 90% of the variation in the features. This is not using the outcomes. You can change that. You can say 95, 70%. You can change it. It turns out that you only need like 30 PCs for this to work really well for the digits. So, but again, you have to compute the PCs on the training data. You cannot do it on the test. So you compute the rotation in the training set, and then that rotation matrix is applied to the test. You can't do the PCA on the whole thing. That's a mistake a lot of people do. They do the PCA first, and then they start their machine learning algorithm. That's gonna bias things. Has to be done on the train set. So this guarantees that. Okay, you can see that we do better actually. It's probably removing noise. That's why probably does better. Some of the PCs take out stuff that confuses you. Okay, so I'm going to just show you random forest because it works also very well. So here's my training of random forest. I don't do PCA here. I shouldn't do with random forest. So now all I do now is I change method to RF. It's going to run random forest. And I get a little bit better, 995. Oh, and I this is just from experience. That would be whole nother training, but I'm trying mtry. I didn't get a chance to explain what that is. I'll say it in one sentence. Random forest does 2 random things: bootstrap, and then it chooses at random which covariates to include in the tree. It doesn't use all the predictors. It says take 5 predictors. Or 15, random, and use it for the cart. So how many? Well, that's a parameter you can change. So from experience, I know 5 through 15 is probably where the sweet spot is. but you can, in your own problem, it'll be different. So it's trying out a few things. This one takes, that one probably takes 15 minutes. You get 95.5. All right. Final thoughts before we finish. Oh, sorry. Okay. I'll give you 4 minutes of important things that you will have to look up more details on your own. Parallelization. Absolutely, you want to do parallelization when you're doing this kind of stuff. When you are doing cross-validation, those are completely different operations. Every MSC is it's completely independent of the other MSC calculation. Do it on different nodes on your computer. My Mac has 12 cores, so I can make it go 11 times faster just by doing that. Caret, being so nice, makes it, if you just turn it on, you do this, Caret just does it for you. Just spreads things around and goes 11, my computer 11 times faster. You all have probably, some of you have better computers than me, so we're going even fast. You have 16 cores, 30 cores, whatever it is. This will do it. You just do that and train will just do the right thing. One little note, always subtract 1 so you can keep browsing Instagram or whatever else you do. You need a core for that, so keep 1 out so you can do other stuff while you wait. Also, so your computer can work at all. Okay, and then the last thing, when it's all done, make sure to turn it off. You're not going to memorize this, but the slides are up, so you can just go and look it up. Okay, that's the one of the things I wanted to say. Last things I wanted to say. The other one is random. One of the limitations of machine learning is interpretation. Unlike regression, where every parameter has a very nice interpretation. Here, we don't even know what predictors we're doing or used. There's one thing we can do, and in different algorithms have a version of this. With random forest, it could say, you can ask it, what predictors were used the most in splits of the trees? So that'll answer that question. Variable importance. It tells you feature by feature, which ones, how often they were used. I'm going to make a plot showing the variable importance, and not surprisingly, the edges aren't used at all, and the center part where you can say it's an 8, 6, you can almost see the digits there, but definitely the center ones are more informative. So diagnostics, very nice thing to do is to look at where you made the mistakes. So these are mistakes where I was the most confident about, incorrectly overconfident. I thought there was a 67% chance this was a 4. I actually don't know what that is. 8 maybe? Maybe 8. Oh, it is an 8. It's an 8, sorry. And I thought it was a 2, 7. But you want like that. I thought this was a 9, it was a 4. That one we can probably do better. I think the reason is because it's too diagonal. So this one, anyways, you get the point. Like from seeing these, one of the things I learned from seeing this plot is that something that might help is it's too complicated to implement with Caret. But if I should take each one of those pictures and rotate it a little bit, just find the best. So I try this and then I rotate it, try again, try again, try again. Because this one, if I rotate it like maybe 10 degrees, it'll be sure that it's a 4. And so every digit you can rotate a little bit and then predict on it. That is actually one of the things that works well for these things. But that inspiration comes from seeing the mistakes. Okay, last thing. These is great ensembles. We're estimating this conditional expectation, and you saw an example where it was like this curvy thing. Now imagine the 784 dimensional version of that. It's be super complicated. You have some estimate of it. It probably has some bias because maybe you over smooth a little bit or whatever it is, or maybe it was too wiggly. Then you have another that you use random forest. Now use KNN, that gives me a different one. And it'll also have biases and errors, but they might be somewhat independent. So what do statisticians do when they have 2 independent estimates of the same thing? take the average. Why not? You try a bunch of algorithms and then you take the average. This is it. Here's the average of K and N and random forest, and we go up a little bit, even a little bit. Not that much, but a little bit. So you can get this to 99% if you like keep at it. Deep learning gets to 99% pretty well too. Point is, now you have all the tools you need to do at least some basic machine learning using R. All right, I'll stop there.
Any questions?
I saw you skipped over it.
Mhm.
Can you just comment real fast on like how you estimate the runtime for
Oh, yeah.
like when you have 200 algorithms to choose from, the runtime could be 1 second to like a million seconds. So
I have the very simple thing is that I do is I run my system time on one. So I don't go train right off the bat. I'm glad you asked. Do not go straight to train ever. Before you go straight to train, try it on one. See, this is one instance, one random forest. This one already takes a minute. I'm gonna do now you start multiplying. You end up, oh, this is gonna be 250 minutes when I do train.
is it always linear or does it depend on the?
Yeah, it's almost always linear because they don't use each other. Yeah. Now, oh, but parallelization, then you divide by the number of cores. Sure. But yeah, definitely do things like this before you go because it's, you don't want to, and most of these things don't give you an update bar. So you'll just be waiting. Absolutely. Thanks for asking. You want to get an idea of how fast it will. And another thing I didn't mention, you would have noticed it immediately is that Carrot doesn't come with all the packages installed. If you want to use random forest in Carrot, you have to install the random forest package. That's in the help. That's in the manual. So for each one of the ones you want to use, you have to go and install whatever. It's in them. It's very clearly delineated in the manual. I think K&N comes with, but I think that might be the only one. Other questions? Ready to do machine learning?
Thank you very much.
All right.